The next video I want to do still concerns transition metal catalysts, and the first one is going to deal with a heterogeneous catalyst. So this is vanadium 4 oxide or vanadium 5 oxide catalyzing the conversion of sulfur dioxide into sulfur trioxide. So what we're looking at is the reaction of SO2 plus half O2 forming SO3. Now this is catalysed by vanadium 4 oxide V2O4 or vanadium 5 oxide. It can be one or the other for the reasons that was mentioned in the last video. So going through the same steps, we've got the overall equation here at the top. The first step that we need to do is write out the redox reaction for converting our catalysts into one another. So if we wanted to convert V2O4, so V2O4 into V2O5, vanadium's balance, one extra oxygen here, so we had H2O here, two H's, so we need two H plus and two electrons. And then to convert the V2O5 back into V2O4, it's just going to be the exact opposite. Okay, so those are our redox reactions for the conversion of the catalysts from one form to the other. Now, what we need to do now is do redox reactions converting species in the actual equation. Now we can see we can easily do one for sulfur dioxide converting into sulfur trioxide. So SO2 gets converted into SO3. We need an extra oxygen on this side, so H2O plus 2H plus 2 electrons. Now we haven't got anything that we can convert the oxygen into, not without needing to add other unusual things. So in the case of oxygen, we just convert it into water. Now I'm not going to do half O2, I'll just do O2. So we'll convert that into water. So we'll need two H2Os and 4H plus and 4 electrons. So those are the routes that potentially our reactants may well take. Just like the last time, we need to pair these up. A catalyst with a reaction equation, but we pair them up in terms of an oxidation for one goes with a reduction for the other. So if we just categorize these, this one is oxidation. Oh, you can't see that, sorry. This one is reduction. So electrons on the right, oxidation, electrons on the left, reduction, and the same with this. So this one is oxidation, this one is reduction. So I'm going to pair up an oxidation with a reduction and the reduction with the oxidation here. So if I wanted to use this one first, it doesn't matter. These equations can occur in either order, as we said last time. So I'm going to do this one. So just V2O4 for oxidation with the O2 for reduction. Still need to make sure electrons balance. 2 electrons in this, 4 in this, so I'm going to double everything in this line. So I would have 2 lots of V2O4 plus 2 H2O plus 4H plus O2. I won't bother writing the electrons down, and that forms 2 lots of V2O5 plus 4H plus, I won't bother writing those electrons down, plus 4H2O. Then because we've got the same species on both sides of the equation, we can cancel out. Subtract 2 waters from both sides. And I've just made an error. That I didn't need to double that. That should have just been a 2. So 2 H2O gets subtracted off both sides. Then 4H plus and 4H plus. So that's a bit of a mess at the moment. So to simplify that, 2 V2O4 plus O2 makes 2 lots of V2O5. That's one of our equations which shows how the catalyst takes part in the reaction. So that's that first one. Now I'm going to look at the other, this one and this one. Reduction with oxidation. Now luckily, 2 electrons in each, so I can just combine the reactants and combine the products. V2O5, make sure you can see that, yet, plus 2H plus, I'll leave the electrons again, plus SO2 plus H2O gives V2O4 plus H2O plus SO3 plus 2H plus. Again, we can cancel further. Subtract 2H pluses off both sides, subtract water off both sides, and to tidy it up, V2O5 plus SO2 makes V2O4 plus SO3. And that's the other equation that you need. Now this one sort of makes sense. You can see to convert, so just move this up, to convert SO2 into SO3 it needs 1 oxygen, or half a mole of oxygen molecules. And so you can see that if V2O5 turns into V2O4, that can supply that 1 oxygen that it needs. But then to reform V2O5, because if V2O5 has turned into V2O4 and supplied an oxygen, it needs to turn back into V2O5, and it gets that oxygen from half a mole of oxygen molecules. So that one sort of makes sense. So it's up to you. You either learn these equations because they are part of the syllabus, or you can learn how to derive them. But this one, it's not too difficult to actually see once you've seen it all put together for you to actually reproduce it. So this is a heterogeneous catalyst because we've got 2 gases as our reactants up here, yet this is solid. So we've got a catalyst which is in a different phase to the reactant. So 2 phases, that's where the hetero comes in. So that's this one for a heterogeneous catalyst, and you need to know this, and you also need to be able to apply it because you could be asked to apply this theory onto a similar scenario. Well, I will next do one on the homogeneous catalyst that you also need to know. Thanks a lot.